Okay, today we're going to talk about forces. Here's the plan. We're going to talk about what forces are. We're going to talk about combining forces. We're going to talk about Newton's first law. Then we'll talk about different types of forces and then introduce the idea of free body diagrams. I know it sounds like a lot, but it shouldn't be too bad. So, what is a force? A force is a push or a pull. It acts on an object. It requires an agent, so something to do the acting. It's a vector, and it can be contact where it requires some form of touch, or it can be long range. And here's an example of a force vector. So we have the little particle at the end. That part represents the object that the force is acting on. Then the force vector comes off of that in like the direction of the push or pull that the object is experiencing. And yeah, and then the other thing we do with force vectors is give them labels. So let's look at this, or these examples. So for this one, because I said there needs to be an object, as an object that is experiencing the force, and then an agent, which is applying. So in this picture, we have this person pulling on this big box. The box in this case is our object, and the agent is the rope, but through the rope, we get the force from the person. So we have a pulling force from the rope on the box. Then another example is this box, these are all boxes, being pushed by this spring. So the box is the object and the spring is the agent. And in this situation, the spring is pushing the box to the right. Then we have an example here of a long range force. So these are contact forces because this one requires a rope. This one requires touching the surface of the box. But this box is falling. And in the process of falling, it is experiencing a force, and that force is gravity. And we refer to this as weight of the object. So in that case, the box is the object, and the earth, which is supplying that force of gravity, is the agent. So usually there's more than one force acting on an object. Generally speaking, there are very few, yeah, I'll get to it. There's very few situations where it's only going to be one force acting. So part of the reason why we start out focusing on vectors is because once we get forces, you have to use vectors. So for example, we have another box, and we have two people pulling on different ropes attached to the box at different angles. And if we just look at the vectors and, make the box this little dot, we have the forces as vectors here, and then we also have the sum of those forces, and we call that the net force. So the net force on an object is the sum of all of the forces acting on it. So now I have an example problem, a lecture problem for you to do. So I'll read it and feel free to pause and think on it. But we over here are seeing two of the three forces acting on an object. And the net force, so the total forces when we add them all up, points right to the left, directly to the left. So we want to figure out which of these is that missing third force that would result in the sum of all of the forces pointing to the left. So you can pause it here, or I'll walk you through the answer. So first things first, in order to get a net force only pointing to the left, we have a couple of things we have to do. We have to counteract the upward direction of this force, because again, it just said all the way to the left, not at an angle. So that means there shouldn't be any force in this up or down direction. And then we have to get rid of all of this force pointing in the right and still have some left over that points to the left. So we can right away eliminate both B and D, because B doesn't have a Y component. So it would still be pointed at some sort of angle. And then D doesn't have an X component. So it would still be pointing to the right instead of the left. And then we'll look at A and C each like kind of separately. So for A, one thing I'm going to do is just kind of some colors here. So this light blue and this light purple are going to represent the forces, force 1 and force 2. And then I'm going to break force 3 into, I'll just say the X and Y components, but also you can think the vertical and horizontal components. So the horizontal component here and the vertical component there. And then we can combine those. So I just am moving them here so that I can bring in the forces we already have. So we have the Y component of force 3, and then I'm just adding the other force that's in the Y direction, which is force 1. And then I have the X component of force 3, and then force 2, which is in the opposite direction of the X component of force 3. So these forces will just sum together. So these two, force 2 and the X component of force 3, those do cancel out. Those are pretty much the same size and in opposite directions, they cancel. But these two, they just combine. So what we end up with first is 0 in the X direction, which isn't what we're looking for, and a really big force in the Y direction. Also not what we're looking for. So we don't want the forces in X to cancel out all the way. We do want that to happen in Y, but we don't want it in X because we want to end up with the net force pointing to the left. Okay, let's do this with this one instead. That didn't click there. Oh, well, it just did it all together. So we have the X component of force of the force and the Y component, and then we'll bring in forces 1 and 2. So force 1 points in the opposite direction of the Y component of force 3, and force 2 points in the opposite direction of the X component of force 3. So off to a relatively good start. Let's look at what the Y components do. Because they're equal in magnitude and opposite in direction, that ends up with the Y component of the net force being 0, which is what we want. So that's good. And then we can look at the X component. So first is the X component of force 3, and then we put force 2, and you can see that there's still some extra pointing to the left, which is what we want. So we end up with the net force pointing to the left, which is exactly what we want. And this one was C, by the way. I don't have the question as the next slide. So anyway, it is the correct answer is C for that one. So now Newton's first law of motion says that an object with no forces acting on it, if it is at rest, it will remain at rest, and if it is in motion, it will remain in motion. So what you want to think about with this really is that forces are required to change motion. Because what Newton's first law is saying is that if there isn't a force acting, whatever our object is doing, it will continue to do that unless a force acts on it. So if it's at rest, not moving, it won't move unless a new force is acting on it. And if it's in motion, it won't stop moving until a force acts on it. So you can also think about something in regular life with this. For example, if you roll a ball across the floor or like the ground, it's not going to keep rolling forever. Like, we know this. It'll stop eventually. And that means there must be a force acting to make it stop moving. So that's just something to think about, and we'll talk more about what that force could be. Now I think I'll bring this up probably again because it's something that people get stuck on. But one of the forces that we want to talk about is the weight force. And weight is not the same as mass. So mass is an intrinsic property of an object. As long as the object remains whole and doesn't like fundamentally change, its mass is constant no matter what else is happening. But weight depends on both the mass of the object and the local gravitational force. So for example, a basketball that we take from Earth to the moon is going to have the same mass on Earth as on the moon, but a different weight because gravity is different on the moon than on Earth. And weight is given with a W, and then M for mass and G for acceleration due to gravity, which you're familiar with now. And so you can also see in this situation that the whole time this force is pointing down, no matter really what the object is doing, because it's always pointing in the like toward the center of the Earth, or the center of whatever object is providing the gravitational force, which will usually just be the Earth. Now there's spring force also. So springs are act in a slightly unique way, and so they have their own type of force and their own equation for force, and it's given by this here. Force spring is negative k times x, where k, that's a spring constant, so that tells you how easy it is to compress or stretch the spring, and then x is just how much it is stretched or compressed. And something interesting about springs is they have a natural length that they want to be at. So the spring force acts when you are changing the length of the spring. So if you compress it, it's going to push out because it needs to get back to its natural length. Or if you stretch it, it's going to try and pull you back to compress back to its natural length. Now there's also a tension force, which really is just, it's kind of, you can sort of think of it as a pulling force, but it requires a rope. So, or a rope or a string, something like that. So someone could pull on an object and there might not be a rope in it, and that means there's not tension happening. But if there's a rope and it's being pulled, there's tension. And tension really just acts in whatever direction the rope is being pulled. So you could also imagine, because we have a sled here, you can imagine someone pulling in the opposite direction. The rope would point the opposite direction. That's the direction the force would point. Another one that we're going to see a lot is called normal force. And it is not called normal force because it's just like the typical force or something. No, it means normal, like perpendicular. So it's saying when you have two surfaces coming into contact with each other, there's a force acting between them, pushing back against each other. So we have this physics textbook on a table, and the molecules within the table are pushing back on the molecules within the textbook. And we're not looking at these forces at the molecular level. We're just looking at it all combined together. But what we will see is that as long as an object isn't falling through another surface, there must be a normal force acting on it. And then again, the thing to remember is that normal means perpendicular. So we have a table that's horizontal. That means the normal force from the table on the book is going to point up perpendicular to the table. So, but if our surface changes, like for example, we have this person pushing against a wall, the wall is pushing back, but normal or perpendicular for the wall is pushing out. Whereas if we were looking at the floor would be pushing up. And then if we're on an incline, again, it's just perpendicular to the surface. So remember, that's what normal means. It doesn't mean just like the typical force. It means perpendicular to the surface. There's also two kinds of friction forces that we'll deal with. So there's static and kinetic friction. So kinetic friction is the friction force that an object that is moving experiences. So we have this child on a sled, and there's friction between the sled and the ground. And this is kinetic friction because the sled is moving. And then we have this really big box, and this woman's trying to pull it, and she's not succeeding. And so this box is undergoing static friction because it's not moving. And so these kinds of friction, you want to think about it as static friction is trying to prevent motion, and kinetic friction is kind of trying to stop motion. In both cases, they point in the opposite direction of either motion or intended motion. So obviously, in this example, we have a velocity vector telling us that the child and the sled are moving to the right. So opposite direction of that is to the left, and that's the direction of our kinetic friction. And this one, in static friction cases, you have to think about what the block would do if, like, the other forces won out against the friction force. And so this woman is pulling to the left, which means if she was successful, the box would move to the left. So the static friction force is acting to the right. There's also drag or air resistance. So this is the idea that when you're moving through the air, because the air is not like it's not a vacuum, like it is a substance, that pushes back against the object. And that is what we call drag. And that's the force. And it also points in the opposite direction of motion. And thrust is another one. So this is you can kind of think of it as like rocket force almost. So what happens is some sort of rocket system, I guess, pushes out exhaust, and that allows it to have a force pushing forward. So that's another type of force. Now I'm going to introduce the idea of free body diagrams, and this is something we're going to be working on because I think this is super important for understanding forces. So one thing we're going to practice both as your activity today and then on Tuesday too, is just identifying the forces that are acting and then also identifying the directions they're acting in. But a free body diagram is where you identify which forces are acting and then you draw those vectors on an XY coordinate axis where the center is just a particle that represents the object. So we have, this is an elevator. It's the elevator box attached by a string or a cable, really. So we have a tension force because there's a cable, and then weight, because it's near the surface of the earth. And because it's not touching any other surfaces that we can tell, we don't assign a normal force to it. So once we figure out, okay, these are the forces acting, and then we draw our coordinate system, and we have to figure out what direction those forces are acting in. So as I mentioned before, weight force is going to pretty much always be pointing down, or at the very least toward the center of the earth, which usually is going to be down. And then tension just follows the direction of the cable. So in this case, the cable is like up. So the forces from the tension is pointing up. So we put the tension force pointing up and the weight force pointing down. And then we just label them the weight force, we give it a W, and the tension a T. And the other thing that we'll do, but you don't have to worry about this one too much yet because we have a little bit more to cover before you really like understand how to assign this one. But if the net force isn't zero, so if the forces don't sum up to be zero, we also just want to label the direction of the net force, and that can just be off to the side. So in this case, we can see the tension force is bigger than the weight force, so the net force points up in this situation. We have another example of this. Sorry, this is like kind of pixelated. So now we have a car that has rocket engines so that it can experience thrust. So it's sitting on the ground. So there's a normal force between the ground and the tires. And then it's near the surface of the earth because it's on the surface of the earth. So there's a weight force. And then there's the thrust force from its rocket engine. So the next thing we want to think about is, okay, what direction do these forces act? So I've already said weight force is going to be down. Okay, check, we've got that. Normal force, it's going to point opposite of, perpendicular to the surface, or to where the two surfaces are interacting. So the ground and the tires. And remember I said that if an object isn't falling through a surface, then the normal force is pointing in the opposite direction. So obviously there's no indication that this rocket car is sinking into the earth. So we can assume that the normal force points up. And finally, the thrust force, that's going to point opposite the direction of kind of like the rocket engine stuff. So that's pointing to the right. So this is what we end up with. We have our normal force. You can write a capital N or a lowercase n, either way. Pointing up, our weight force pointing down, and then our thrust force pointing to the right, and our net force, which is just from the thrust, because normal and weight forces are equal in magnitude and opposite in direction, so they cancel out, leaving us with just the thrust force. Okay, now one more example here. Feel free to pause and walk yourself through this if you want, but I'll just talk you through it too. So we have a book sitting on a table. Let's think through the forces acting in this situation. It's on Earth, so there is a weight force. Yeah, weight, cool. And it is sitting on a surface. It's on the surface of this table. And as we've been saying, if it's not falling through the table, there is a normal force holding it up. So there's also a normal force. And then we can think about some other things. There's no spring, so there's no spring force. There isn't any rope or cable that we can see, so we can eliminate tension. It's not moving, so forces like drag and kinetic friction aren't acting. And thrust also isn't acting. So I think we are safe with just calling this experiencing two forces, weight and normal force. So the next thing we want to do is think about the direction of those forces. So weight force is going to point down toward the surface of the earth. So let's put that here. And then normal force is perpendicular, so it should go either up or down. And we know the book isn't falling through the table, so it should point in the opposite direction of the weight force. So our normal force is pointing up. And this is another version of a free body diagram where we just drew it on the picture of the object, but we could also have just made a dot and an XY coordinate plane and drawn our forces on there. Okay, well, that is your intro to forces. We will be spending a lot more time with this. So I hope you are looking forward to it. I am. I like forces. Have a great day.